Okay, thanks very much for the introduction. So today I'm going to be talking about coronal heating, and I know the purpose of these talks is to give a kind of general introduction to different subjects in the field of solar and coronal physics. And coronal heating can be a little bit of a dry subject for some, because it's very theoretical, partly because we've got no kind of actual direct direct observations of coronal heating, so there's a lot of theory trying to actually explain observations. So what I thought I would do today was give a very quick history on the subject of coronal heating and the coronal heating problem and how it came about. I will show some observations, just a few which are kind of pertinent to the subject. And although there are many mechanisms that have been put forward for heating the corona, I'm going to discuss two of the more popular methods that are put forward to actually explain the coronal heating problem. And that's not to say that these are the only two. There are many ideas out there, and simple Google searches will actually get you lots of results, but I don't have enough time to discuss them all, and there's a lot of theory behind a lot of these things. So if you want to learn more about the subject, you just do a Google search, you'll find a lot of different ideas out there. So to begin with, I thought I'd begin with a very, there we go. I thought I'd begin with a very short history of the coronal heating problem. And in some ways it's quite a new problem, and in other ways it's actually been around for quite a long time. So it's about 120 years ago that we started to make more detailed observations of the sun, and we've been observing the sun for a long time for our history, but when we started to get more sophisticated telescopes and cameras. And it was in the 1890s that we're actually able to actually start looking at the solar surface and get an idea of temperatures that are involved, and it was in the 1890s that we actually made measurements of the solar surface temperature to be around 6,600 Kelvin, and this was using the newly discovered Stefan-Boltzmann law back then, and it was generally assumed that this was made of gas. And as I'm sure many of you know, the solar photosphere, that's what we consider the actual physical surface of the sun, radiates like a black body. And its spectrum gives us an idea of the temperature, and we also see these kind of like dark Fraunhofer lines which reveal its chemical composition. And at this time, we didn't have any space-based instrumentation. It's very hard to observe the solar atmosphere due to the bright solar surface. And one of the main ways that we're actually able to observe the solar atmosphere was through total solar eclipses, when the actual disk of the sun was obscured. And using spectrographs, this is back in the 1870s now, pointed at the corona, we were able to see, observe the spectrum of the atmosphere, and we saw these Fraunhofer lines, and we also saw some unknown bright lines. And so during an eclipse in 1869, there was this emission revealed in the green part of the spectrum, and this was named coronium, and further reading can be found here. These slides should be online somewhere, so you can get the link from there. And it was in 1939 that Grotrium, if I can pronounce the name correctly, showed that this emission line is due to the iron 14, due to iron 14 emission. This is an atom that has lost 13 of its 26 electrons. And using similar spectrums, he also showed that there were other lines that are identified, such as calcium 12, iron 9, and iron 13. And to remove this number of electrons, you need a very high temperature plasma. And it actually demonstrated that we were seeing a solar atmosphere with a temperature greater than 1 million Kelvin. And this is the kind of the start of the coronal heating problem. Again, there's a wonderful web page on the Cambridge website. I encourage you to go there if you're interested in the history of this subject. In the 1940s, the intensity of the steady component of solar radio emission was explained by a 10,000 degree solar chromosphere. That's going to be the lowest level of the solar atmosphere, which I'll describe afterwards, and also a 1,000,000-degree solar corona emitting in long wavelengths. And it was predicted that the extremely hot solar corona would also emit in X-rays. And I've just overlaid over the back here, this is a contemporary image from the SXT soft X-ray telescope showing the sun in X-rays. So that's where we are in terms of we got this idea of this hot corona up there, and it's at this point we have to kind of like define what is the corona. So the sun is surrounded by this atmosphere of gases, and the corona is the outermost layer of that. The corona has a temperature 3 to 4 orders of magnitude greater than the visible surface, and as I said before, due to the relative brightness of the sun's surface, it's only visible from Earth during total solar eclipses. However, we have got around that in recent years by using space-based observatories. Now, if you guys came to my previous presentation, you might recognize this slide, so I'm not going to go through all of this. This is just a very quick kind of schematic of different ways we've observed the sun throughout the years. And I want to highlight some of the later observations down here where we've been observing the sun in the EUV part of the spectrum and the X-ray part of the spectrum. And this is where we're actually able to see the hot part of the solar atmosphere without seeing the cooler solar surface. So I like this slide here. This is showing most of our contemporary full-sun images observing the sun right now and also in the future with Solar Orbiter up here. And what I've put up here is a series of images of the sun from EUV observatories, and I've also included an X-ray up here on the left-hand side here. This is working. This is from SXI, and there's some of the cooler AIA passbands here. And what you're seeing here are all the the observatories observing the full solar disk in the EUV. And so we're observing hot parts of the solar atmosphere, and we're observing it in these wavelengths down here, starting with SOHO EIT, which has been observing now for over 2 solar cycles, it's over 22 years. We've got stereo observations, sorry, I should say that SOHO EIT are observing the L1 point. Stereo EUVI is moving around the sun ahead and behind of the sun, of the Earth in its orbit. We've got the Proba 2 satellite here, which is hosted here at Rob, SDO AIA with all these different passbands here, and the newly launched GOES-R-SUVI mission. And finally, in the future, we'll have the Solar Orbiter FSI images to help complement all of this. And what these are showing are different views of the hot solar atmosphere, and to give you a better idea of what they're observing, here you can see the range of temperatures here. And I realize these images are small, but you can get an idea of different structures that we can see in different temperatures. And we're seeing bright emission from different structures on the sun, ranging all the way from around 50,000 Kelvin up to around 10 million Kelvin. I should just indicate that a lot of these passbands are quite broad, and so we're not necessarily always seeing 10 million Kelvin or 6 million Kelvin, and it could be emission from different parts of the temperature range. So, and just to give you, I like this video here, which is from 6 of the AIA passbands, and it's showing an eruption off of the southeast limb of the sun in 6 different passbands here. So I've kind of indicated the temperatures up here. So this kind of like blue colored one here is showing emission, which could be up to around 10 million Kelvin, and the coolest one down here is this yellow one, the 171 angstrom passband, which is under 1 million degrees. And what we can see is, with this particular eruption here, we see emission passing through all of these temperature ranges, all the way up to this very high temperature here. So how do we define the corona? Well, it's intrinsically linked to inside the sun, because that's where the energy is coming from, and the lower atmosphere as well. So this is just a schematic of the sun. We start in the core where we have our nuclear fusion processes, and then as we move out from there, the density drops and fusion can no longer be sustained, and we move into the radiative zone where there's mainly radiative processes going on. The temperature and densities drop even further. We reach a point here known as the tachocline before we move into a region known as the convection zone. This is where we see hot plasmas getting kind of churned up, and the magnetic fields of the sun are believed to be generated in this region and across the tachocline as the plasmas move around and generate these magnetic fields. This heavy line that you see around the edge indicates the photosphere. This is the visible surface of the sun, what we like to call the visible surface. Then we move into a very small region known as the chromosphere, and this is when we're in the solar atmosphere, and we begin to see temperatures jumping. Oh, I should also indicate when we start in the core, we've got temperatures of 10 to the 7 Kelvin. They drop as we move through the radiative zone, through the convective zone, reaching a minimum around the photosphere, 10 to the 4, 10 to the 5, 10 to the 3, 10 to the 4 Kelvin. But then we move into the chromosphere, and then we begin to see temperatures increasing again. They go from 10 to the 4, 10 to the 5 Kelvin before we hit the corona, and we start to see temperatures again of exceeding 1,000,000 degrees. And if we just focus on the atmosphere, is what we can see here. This is the photosphere around here. This line here is showing the temperature profile. This line here is showing the density profile. And what we see as we move through the solar atmosphere, we see this large jump in the temperature. We see a gradual increase, first of all, in the chromosphere, and then in the transition region, we see this huge jump in the temperature, and before we move into the corona, where we see it growing even further. Meanwhile, the density is dropping at the same time. And so, with the coronal heating problem, there's a question of how is the energy moved from inside the sun through the chromosphere and deposited throughout the chromosphere, the denser chromosphere, the transition region, and the corona. And this is the coronal heating problem. How are we able to transfer the energy into these regions? This can't be done through just basic conduction and convection or radiation due to the densities, the drop in densities through these regions. So I think that a review paper by Coronal and de Motel, they kind of encapsulate the problem nicely in this kind of quote which I've put up here. So what they say is, for decades the problem has been known as the coronal heating problem, but it's now clear that the coronal heating cannot be treated or explained in isolation, and that the heating of the whole solar atmosphere must be studied as a highly coupled system. The magnetic field of the star is known to play a key role. And I kind of highlight this here because I'm going to talk a lot about magnetic fields, and it's a very important thing, and it's intrinsic to most coronal heating mechanisms. The question of which mechanism or mechanisms are the dominant supplier of energy to the chromosphere and corona is still open. And even though, so this was wrote in 2012, and I don't think we're any closer now to actually solving this, and you know, we've been studying this for 50, 60 years, even longer now. And just to finish up, so one thing to highlight here is if we look at this plot here again, and we look at the density and the temperature structure, we see the chromosphere has very different plasma properties to the corona. And so explaining the heating of the solar atmosphere is now recognized to be considerably more complicated than had previously been anticipated throughout the 20th century. So when we look at heating the corona, we have to look at a whole multitude of different length scales in density, temperature, and actually in kind of physical length of magnetic field structures. So it's a very complicated problem that we're trying to solve here. What kind of energies are we talking about? So this is a relatively old paper which is still referred to today. It's from 1977 with Noyes. They made an assessment of different regions of the corona and chromosphere, and they tried to parameterize it in terms of how much they were emitting, and therefore how much energy is actually required to be given to these different regions. And this is a combination of conductive and radiative estimates. Now, I apologize for the units up here. This is kind of like standard in coronal physics, where they use ergs to the centimeters to the -2. Just down here, just a little kind of cheat. 1 erg is 10 to the -7 joules. So you can kind of get a rough idea of what these are. And the kind of numbers that we're looking at here, chromosphere, we're looking around 10 to the 6 in coronal hole regions and 10 to the 7 in active regions. And then in corona, this is slightly lower because we're in a lower density region, and then this kind of moves out, it drops even further as we move into the solar wind. And so any coronal heating, atmospheric heating mechanism has to supply enough energy to account for these. I want to take a step back now and just show this video of the sun, and it's partly because I like it, and it's from probability swap. But the bit that I like about this is it highlights the magnetic field structures on the sun. And the coronal heating mechanism is going to be linked to the magnetic field structures on the sun, and I've just highlight some of the different length scales and different magnetic structures that we can see here. So first of all, we kind of got like these kind of dark regions at the poles and some other ones here. And these kind of indicate the coronal hole regions. These are called open field regions where the magnetic field reconnects a long way from the sun, effectively at infinity. Then we look at some of these like active region here, and we can maybe make out some kind of these like small loop structures in here, some very small loop structures. We see some trans-equatorial loops, I believe, in some of these images. They should be connecting from the different hemispheres. We see a lot of these large opening fan structures. And the point to take away from here is we're seeing a lot of different magnetic field structures here of different sizes and different length scales. Bear in mind that this is from SWAP, which observes at just under 1 million degrees. We can see these kind of like bright hot regions, and we see some of these darker cooler regions here. So there's a lot of temperatures in there. And a coronal heating mechanism has to try and explain some of these observations. So first of all, the EUV, UV, and X-ray coronal images and magnetograms indicate that coronal heating is a magnetic phenomenon. And the heat mechanism must explain both how the material fills the loops and heats it to coronal temperatures, as well as background emission. And this is just kind of like a general kind of like cheat sheet rule we have down here. In general rule, the hotter the loops, the stronger the regions of magnetic field they're associated with. Now, these magnetic loops are emerging from inside the sun. They're generated, we believe, in the tachocline and throughout the convection zone, where they're wound up and they kind of pop out throughout, and they vary throughout the solar cycle. And so the magnetic fields that we're seeing in the solar atmosphere are linked to what's happening inside of the sun. And the photospheric driving, this is the movement of the foot points of these loops, create a complex topology and geometry in the solar atmosphere, and create this range of different sizes of magnetic loop structures. And so what's happening inside the sun and this driving of the magnetic field structures is linked to the coronal heating problem. And I like this cartoon here from Peter back in 2001, and just kind of indicating the different magnetic field structures. We've got some these kind of like tight, small-scale loop structures at the base here, and then this is kind of in the chromospheric regions, possibly pushing into the low corona. And then as we move out through the corona, the magnetic field structures expand out into what become the solar wind. And we've also got some large-scale funnels and loop structures here. And we should say in the lower atmosphere, the magnetic field is concentrated into little small flux tubes. This is on the order of kilogauss, and then these expand out in the chromosphere and in the transition region. And these small loops kind of form this low-lying magnetic carpet. The part of the internetwork flux extends above the carpet and spreads out in the corona, and the magnetic field in the quiet sun is a mixture of network field and survive in inter-network field. So we're kind of seeing a mixture of all these different structures here moving out through the corona. And what we can do is we can actually look at the movement of, just make a basic assessment of how the foot points of these magnetic structures are moved around and the magnetic energy that's coming through from the lower atmosphere, and just using a very simple kind of Poynting flux equation. If you want more details on this, go to this paper here. You can expand this and you look at the energy that's generated from the movement of magnetic fields from the lower atmosphere, and from the Poynting flux per unit area, we get some estimates of the energy that's delivered from the lower solar atmosphere, from the solar surface, through the solar surface into different parts of the solar atmosphere. And we come up with these estimates here, 2.5 to the 10 to the 7, again in ergs, I'm afraid, and in active regions, 1 times 10 to the 9. And if we compare them to the parameters I showed before, these are what we need to actually generate this is the energy that we have to put into the system to generate the observables that we see on the sun. What we can see is, just by looking at the Poynting flux from these regions, we can amply cover the energy required to make these observables. And so the energy injected by the movement of these foot points is more than enough to supply the energy into the chromosphere and the corona. But the trick is, how do you actually get the energy out from these movements? And that's when we start getting into the territory of coronal heating, because it's enough to put the energy there, but how do we actually liberate it? So, as I said at the beginning, there's a huge number of mechanisms that have been put forward and suggested, and I don't think that there's ever going to be one answer to this. It's going to be a selection of different models, and they're all going to contribute towards the coronal heating problem. And to be honest, most of them are probably linked. And I haven't got time to go through all of them, and I'm going to cover a couple of the basic ones. But I suggest looking at this selection of papers here. I've put DOIs when they're available, and if you're interested in this, you can go and grab these you'll find them on NASA ADS and things like that. And there's some very nice, like, living reviews by Fabio Reale. And they cover a multitude of different coronal heating mechanisms. And as I said, I'm just going to cover 2 of them now. And I encourage you, if you're interested in this, to seek out the links that I put there for further reading. So the ones that I'm going to focus on are waves and magnetic reconnection. So the energy that heats the solar atmosphere, as I said before, kind of comes from the lower atmosphere through the convection zone, and this energy manifests itself as waves and reconnection. And we have evidence where we see waves in the solar atmosphere, and we see evidence of magnetic reconnection in the atmosphere. But I'm going to talk about these a bit more, but they both have problems as methods for heating the solar atmosphere. So waves, we're more familiar with this idea of a wave because we see it in different aspects of our life. The idea of magnetic reconnection is that the magnetic fields get wound up and they get stressed. It's creating current sheets throughout the magnetic structures, and these are liberated, releasing energy. Now, which of these mechanisms is most important for chromospheric and coronal heating is still very much open to debate. So, as I said before, the mechanical motions from below the photosphere lead to a heating mechanism, and these can be broadly separated into slow, long timescale motions, which result in a quasi-static stressing of the field, and a fast, short timescale motion, which is generating waves which permeate the coronal magnetic fields. And the dissipation of these magnetic stresses, so how the energy is actually got from the fields, from the field lines, is through one of 2 mechanisms which are separated into DC heating and AC heating. And so DC heating describes the dissipation of magnetic stresses which is typically manifest as current sheets. So we wind up the magnetic fields, we get opposing magnetic field lines, and then we get small current sheets formed between them, and this energy is released mainly through magnetic reconnection, known as DC heating. Here, this is kind of a rough schematic here. You have two field lines, you wind them up, reconnection occurs, and energy is released at this point. And then secondly is the dissipation of waves, and this is referred to as AC heating. And I'm going to start off with just a very kind of quick run through of DC heating and what it's all about, and then I'll move on to the AC heating mechanism. So we begin with DC heating. As I said before, we see the flux emerging from the photosphere. We see coronal loops being generated, connecting new flux features to previous ones. So you've got magnetic fields coming through from below, pushing into magnetic field structures already in the solar atmosphere. And these loop structures then create subsequent loop structures. And the only way that this can actually happen is through some form of magnetic reconnection, which allows this kind of global restructuring of the magnetic field. The foot point motions perform work on the coronal magnetic field and increase its free energy at a rate given by the Poynting flux through the base. And so this is, again, the basic idea of magnetic reconnection here. If we imagine that I'm tracing out some of these field lines here, within these flux tubes, within these monolithic flux tubes, there's believed to be lots of small strands, and through recent observations, this seems to be a fairly safe assumption. And what happens is, as we wind up the foot points, we're able to twist magnetic field lines around each other. And what happens is, as we do this, we get field lines of different orientations being generated, and with these, between these, we generate small current sheets. And here we can see a cartoon of what's happening with 2D reconnection. And what we do is we force magnetic fields of opposing polarity into what's known as this kind of like X point here. Reconnection happens, so the field lines are broken. And when they're broken, they liberate energy in the form of thermal energy and kinetic energy and high energy particles here. So we've got the field lines being forced in here, here, and here, and then through this region, reconnection forces the field lines out of the sides here. And this is only a 2D cartoon of what's going on. These kind of ideas have actually been championed since the 50s and the 60s as a way of actually releasing magnetic energy into the solar atmosphere. And it's considered the source of heating from many dynamic processes, such as flares and bright points, not bright pots. There might be bright pots as well, I don't know. So it's been, the idea has been well developed in 2D, and it all started with this kind of Sweet-Parker model of reconnection in 1958, where we just force field lines into a single point, and reconnection occurs, and we have this reorientated magnetic field and energy, and thermal and kinetic energy. But it was found that this mechanism was quite slow, and this was improved upon by the Petchek model of reconnection, where it increased the actual size of the region you're forcing the magnetic fields into. And by doing this, it actually increased the speed of this 2D reconnection. And there's been more iterations of this. There's more than what I put up here, but Priest worked on this a lot throughout the 80s and the 90s. I recommend looking at this book here by Priest and Forbes from 2000 for a kind of thorough review of 2D reconnection. But the 2D models only kind of cover a small part of magnetic reconnection, and the solar atmosphere is a 3D structure. And in recent years, we've actually got the computing power to actually start building 3D reconnection simulations. And There's many of them out there. I'm just going to just show you the kind of the basic kind of concept there, where you have in this 3D reconnection model, you get the idea, this concept of a null point, and you get a structure where you get a magnetic fan structure and a magnetic spine, and so you've got two families of field lines that actually pass through the null point. And these are the spine field lines and the fan surface, and this actually achieves three types of reconnection at the null. This movie is not running, I'm afraid, but it was just a simulation from a model by Galsgaard. And we see spine reconnection, fan reconnection, and separator reconnection. And one of the advantages of the reconnection idea is that it can actually occur at many different heights and at many different length scales. And one of the best ways that we have evidence of magnetic reconnection is through the observation of solar flares, which is the rapid release of energy, and this has been observed over many length scales. And what I'm showing you here on this plot here is it's showing flare energy along the bottom axis and the flare frequency up the side. And so what we find is we have a lot of observations of large flares, which we see all the way up to our kind of X-class flares. And as we move down to smaller scale flaring regions, we see more of those. And if we move into the microflare region, we see more of those. And then we start approaching what's called the nanoflare region, where we expect there to be lots of them. However, we don't have any direct observations of nanoflares because they're too small. They're below our current imaging resolution. So we actually make assumptions on how many of these nanoflares we expect to see. And in the past, people have made various surveys of assessing numbers of different numbers of flares. So in hard X-ray observations, they came up with a power law of like 1.5 from this flare energy, flare frequency. Soft X-rays is 1.7, in the EUV 1.8 and 2.5. And although we don't have observations of nanoflares, what we need is for there to be enough flares in the solar atmosphere to actually heat the corona and the chromosphere, we need this powerful power law to hit a value of around 2. And as you can see from these values here, it's not quite hitting this in the larger flare regime, possibly from some of these EUV observations here. But one thing that should be said, it's not clear if what's happening in large flares, if reconnection in large flares is the same as what's happening in the nanoflare reconnection. So this is an open argument against the flare idea of heating the solar atmosphere, or the reconnection method of heating the solar atmosphere. So then we move on to AC heating, and so this wave heating. And so the convection that stresses the chronomagnetic field generates a large flux of upward propagating waves. And these are seen through acoustic, ALFVEN, slow and fast magnetosonic waves. And mode coupling and other processes transfer energy between the different types of waves. And so the mix of different waves changes as a function of height as we move through different temperature and density regions. And only a small fraction of the flux is able to pass through the very steep density gradient that we actually see down here, and temperature gradients in the chromosphere and the transition region. The acoustic and slow waves seem to steepen into shock waves and become heavily damped, while fast waves are strongly refracted and reflected. And so it's only the ALFVEN waves that are able to penetrate higher up into the corona. And these are waves that travel parallel to the magnetic field, the direction of them. And they do not form shocks since they're transversal, and their energy is, again, this is an autocorrect here, conducted along the magnetic field line rather than being refracted across it. And so with the acoustic waves, this is sufficient for chromospheric heating. The convection generates acoustic waves propagating upwards. These steepen into shock waves or reflected by density gradients, and they're able to actually deposit their energy in the lower chromosphere. But what we're kind of interested in is these ALFVEN waves, which have the potential to travel into the corona and the outer solar atmosphere. So we believe that there's significant transmission of ALFVEN waves. We believe that significant transmission is possible, but only within these within narrow frequency bands, which are centered on discrete values where loop resonance conditions are satisfied. And enough flux may pass through the base of active region loops to provide their heating in these kind of hot active regions that we see on the sun. But this is not the case for a lot of the shorter loops that we see. We have recent high-resolution observations showing evidence of waves in the corona, prominences, plumes, and the corona. So we do see waves throughout the solar atmosphere. And flare-excited waves in loops, fast kink modes, etc. And the feet of long loops show evidence of slow waves. And we also see evidence of CME/flare triggered global waves, also known as EIT or EUV waves. And these are believed to have fast and slow components. But we're still left with the question on how is the wave energy converted into heat? And a heating theory based upon waves has to come overcome several obstacles, which I've listed here. And again, this is from Coronal and de Mortel's review paper. And what they say is, first of all, waves must be generated in the solar surface layers. Number two, sufficient energy flux has to be transported, as only a fraction of the wave energy will be transmitted into the outer solar atmosphere. It won't make it through the chromosphere and through the high density and temperature gradients. And three, the waves have to dissipate efficiently to convert the energy flux into heat in the right place at the right time. So we look at these questions and how the wave heating theory stacks up against this. So number one, waves be generated in the lower surface layers. So solar convection generates this mixture of upward propagating waves and an energy flux as big as this 10 to the 7 ergs per centimeter squared per second. And this would be more than adequate to actually heat the lower solar corona and the chromosphere and possibly the corona if the energy could be deposited there. Two, the sufficient energy flux has to be transported, so it has to get through the lower solar atmosphere. And this is not so easy to satisfy, since most of these magnetoacoustic waves do not propagate into the corona due to the reflection and the refraction off of the density and the temperature gradient seen through the transition region. And also, we believe that mode coupling is expected to take place in these regions where the sound and ALFVEN speed are approximately equal, which reduces the actual flux even further, reaching the corona. ALFVEN waves, on the other hand, are generally seen as very efficient carriers of energy over large distances. And so this is a possible viable mechanism of getting the wave energy into the outer solar atmosphere. And if we look at the final question, the final point that the wave heating mechanism satisfy, the waves have to dissipate very efficiently to convert the energy flux into heat in the right place at the right time. And as I just said, the ALFVEN waves are a possible mechanism for heating the corona. Their weak damping makes them problematic as a coronal heating mechanism. So how we actually kind of damp the waves and deposit the energy in the outer solar atmosphere. But since then, theorists have developed a variety of mechanisms which are likely to actually enhance the dissipation of ALFVENic waves. And this is done through mechanisms such as resonant absorption and phase mixing. And both resonant absorption and phase mixing are based upon the property that in an inhomogeneous plasma, individual surfaces can oscillate with their own ALFVEN frequency. and on a specific magnetic surface. An incoming wave motion can be in resonance with local oscillations, which allows the transfer of energy from large-scale motions to smaller length scales where dissipation can become more effective. And this is similar in the phase mixing idea of how ALFVEN waves on neighboring field lines gradually become out of phase, again generating large transverse gradients until dissipative length scales are reached. So I've just kind of put forward two of the basic ideas of behind AC and DC heating. There's a lot of literature out there and a lot of theoretical ideas, which if you're interested, I encourage you to look into. But I very much doubt that one of these mechanisms by themselves is going to be heating the solar atmosphere. And along with other heating mechanisms, it's probably going to be a contribution from both of them. And there's increasing evidence that both AC and DC heating types of heating can actually work together, where you can see from magnetic reconnection, you actually get jets and waves generated from the regions, which help with the wave heating idea. And then these waves can also affect surrounding magnetic structures and induce current sheets and reconnection. So they're probably intrinsically linked, both of these different methods. So we're not, at this moment in time, we're not close to actually answering the coronal heating problem, and there are several open questions, and I'm just going to present a couple of conclusions of what we have seen so far. So I showed two main mechanisms of heating the solar atmosphere. The first was through magnetic reconnection and flares. And firstly, are there enough flares? I showed you that power law of larger flares in the solar atmosphere, and we still don't know yet if there are enough small flares throughout the solar atmosphere to actually heat to heat the whole of the solar atmosphere. And secondly, are they ubiquitous throughout the atmosphere? When I showed you these images of magnetic loop structures earlier, what I should have said to you was the loops that we see here are the magnetic structures which have got hot plasma on them. And there are going to be plenty more of these magnetic field structures which don't have hot plasma on them, and therefore we can't see them. And we've also got this kind of like background diffuse emission as well. Are there magnetic fields penetrating all these regions, and is magnetic reconnection going on and actually heating these regions of the solar atmosphere? And it's not clear. Secondly, can waves deliver sufficient energy flux to the corona? This all comes, we see that there's ample motions coming through the lower solar atmosphere, but it's not clear how the waves actually break in the outer solar atmosphere, how they actually deposit their energy. So can they reach the upper corona, and is there enough of them to actually heat these regions? Okay, as I just said, can we actually treat the distinct coronal loop structures, these kind of like, this is an X-ray observation here, so you can't really see the loop so well. You can see maybe some structures in here. Are they distinct from the background diffuse corona? And are there different classes of loops that are actually heated in different ways? Is quiet sun heating, so these are the kind of like the darker regions that we see around here, are these regions heated in the same way as active regions? And it's not clear how the AC and DC mechanisms actually work together. We actually have a surplus of heating mechanisms ranging from radiative heating, we have gravitational heating, and various different ways of explaining the DC models. This is the reconnection models and the wave heating models with abundant different parameters. And I don't think any of them have adequately explained how the atmosphere is heated on its own. And you can see this papers by Mandrini and Ashwandhan. And Ashwandhan's book on the solar corona has got a really good chapter on this. and I'd encourage you to look at that. And I just thought I would finish up with conclusions and what we actually need to maybe help solve the coronal heating problem. So this is like a solar physicist's dream, what we would like, and of course it's always like high resolution images and high resolution magnetographs and spectrographs. We would really like some in situ measurements. That would be very nice. Just fly something straight into the sun and we can get some accurate measurements of the magnetic field, the densities, and then what these actually help with is constraining our models, and they actually give us tangible measurements that we can actually prove or disprove our models with spectrographs or any method of actually measuring motions in the solar atmosphere. These are very important for looking at the wave heating mechanisms, but they're also useful for looking at jets that can be generated from magnetic reconnection. So yeah, higher resolution, more magnetographs, more spectrographs, and in situ observations. Data analysis. So when I talked a little bit about magnetic reconnection, I started off with the idea of 2D magnetic reconnection, and that was where our theory was at the time, and also what our simulations could actually produce results with. And as our computing power got better, we were able to actually build these 3D numerical simulations. But we're looking at a multitude of different length scales, and the computers aren't quite there yet to simulate the total solar atmosphere on all different temperature, density, and actual length scales. So we need to actually improve our computing power and improve our models to actually help us understand what's going on. As I said before, in situ heating or direct and ultimately we're looking for direct or indirect evidence of the heating. So evidence of the reconnection on small scales or evidence of the waves depositing their energy in the solar atmosphere. And again, observing reconnection would be one way forward with this. So I've got to 45 minutes. I'm going to stop there and ask for any questions. Thank you.